Hey everyone, in this video, I'm going to walk you through this document on aircraft performance equations. So ideally, if we were in class, I would ask you to do this. We would do this in class as a exercise where you basically derive these equations by yourself. But well, again, in the interest of time and interest of us covering the required materials, I kind of created this document, and all you have to do is go through this document by yourself and try to learn how different terms connect with each other, how equations of motions apply for an aircraft, and how specific things like wing loading and thrust loading are related to each other. Okay, and if you have any questions as you go through this document, just feel free to let me know, and feel free to post your, or feel free to email me, text, a call, whatever that you need to do to get hold of me. Okay, because it's important that you understand what goes on in the aircraft performance. Okay, so this again, there's a lot of equations here, but again, I can promise you that if you just take uh, at least an hour, print this out, sit and go through this document, I'm pretty sure you will understand every single equation in here because everything is grounded on simple Newtonian physics, F equals ma, and that's pretty much everything there is to this, to this aircraft performance, right? So what we're going to do is, in this video, just I'll briefly walk you through the process. I'm not going to go over all the equations here, but I would ask you to spend at least an hour and a half going through the equations in this document. And also, if you want to see the videos that I've created under for these performance. Um, all of them is under the reference tab in the lessons page for this week. Basically, this is a topic that I started covering in my Intro to Flight course. Some of you, when you took my Intro to Flight course, it was primarily theoretical, but last semester in the spring of 2020, I started redesigning my Intro to Flight to basically account for like the performance, because we are trying to design an RC airplane. And in order to do that, in order to design even an RC airplane, we need to know the performance metrics, right? So think about now we are going to design like full scale airplanes. So and for that we absolutely have to know about the aircraft performance and how it influences aircraft design. Okay, so that's one of the reasons why we start this course with an aircraft performance, because you will get to see what controls the rate of climb, what controls the turn, what controls the loading, what controls the range, etc., etc. Okay, so again, so if you look at, the document starts out with a free body diagram of an airplane at an angle of attack, correct? Well, here you resolve the forces in X and Y, and you basically get this. So this is like the master equation, and then we assume what is called the unaccelerated flight, where there's no acceleration, which is dv by dt goes to zero. The first equation here boils down to this, and then in the end, you will get thrust equals drag, lift equals weight. Well, that's great, right? That's basically your cruise condition when there's no acceleration happening. Well, it also assumes that the climb angle is zero, alpha is zero, and etc., right? But that's basically, this is the scenario here. Well, if it's accelerating, then this is the condition that you get, right? So again, I'm going over like an overview of this document, but if you go through each and every equation, again, it's pretty self-explanatory. Again, if you have any questions on this, please feel free to let me know. All right. So, and you have the thrust required and level and accelerated flight. This is very important because again, this is exactly why we need to look at performance. Because if you were to design an airplane, which you are going to, how on earth are you going to know how much thrust your airplane requires? Right. Again, you see why we are learning this. This is the reason why we are learning this the first time, because or which were the why we are covering this in the first couple of weeks, because these equations are fundamental for an aircraft design process. Okay, so again, in cruise condition, well, thrust by weight equals drag over lift, right? It's exactly what we found before. When you solve all of this, you can find the expression for thrust required. Now you put the components of drag. You have the zero lift drag coefficient, induced drag coefficient. right? I mean, here's a table for the Oswald efficiency factor. All of this, you should be, you should know what these are because you should have taken intro to flight or aerodynamics, okay? Um, and then, you'll get an expression for the thrust required here. Well, which is pretty great, right? This is the thrust required. As you can see, there's a lot that goes into here, correct? But again, in a propeller aircraft, the thrust required it's not, it's actually sort of like meaningless because in a propeller aircraft, what produces the thrust is the power of your propeller, okay? So that means for a propeller, if you're going to design a propeller driven aircraft, then you should not be concerned with thrust required. What you should be concerned with is the power required, okay? And more importantly, what is called the available power. Well, an engine can only produce so much power, correct? That's basically your available power, and your thrust available depends on the power and the velocity, right? And the free stream velocity. That's very important, okay? So, and the available power depends on some efficiency. Again, engines are not completely 100% efficient, correct? There has to be some propeller efficiency. There has to be some engine efficiency that needs to be taken into account, right? And the available power is basically the efficiency times the shaft power, correct? Again, this is one of the reasons why you have to compromise between different different fields, and you have to know something about everything. Right, something about aerodynamics, something about propulsion, something about structures, something about stability and control, etc., etc. Okay, so and you move on to finding the minimum thrust required. I basically mentioned all of that in here. Um, right? And then we want to finding CL and CD at minimum thrust, right? For example, what this means is that say you're flying an aircraft and you want to conserve fuel, right? And you want to orient your aircraft attitude in such a way that you minimize the fuel consumption and you are operating under minimum thrust required condition. In order to do that, you have to change the attitude of the aircraft in such a way that you obtain a CL and CD which can sustain cruise condition, correct? That's exactly what we are finding in here is that we are finding what is the CL and what is the CD that we're going to get at minimum thrust condition. Okay, so as you go through this process, you will see again this is the CL at minimum thrust, which is basically square root of CD naught by K. It's very interesting, right? The minimum thrust condition depends on the zero lip drive coefficient. Pretty cool, right? Now you can find an expression for max L over D in terms of CD0 and all that. And then, once you're done with thrust, for a propeller aircraft, as I said, you primarily deal with power. So you have the power required right here. Um, and then we have the velocity and minimum power, CL at minimum power. So you have the thrust required divided by the maximum takeoff weight. So this is basically what we call the thrust loading, and this is what we call the power loading, which again is going to be your constraint equations. Okay, so again, when we do with jet engines, well, you just have to worry about thrust. You don't have to worry about power. Well, you may have to worry about it, but not as much as you do in a propeller-driven aircraft, right? So even the constraint equations, the only thing that changes is the thrust to weight ratio for a jet aircraft, and for a prop aircraft, we have power to weight ratio. Okay. So here's kind of the summary of equations for the relevant to cruise conditions. But again, so guys, don't just go with this table. I would urge you to go through this derivation process and truly see if you can truly understand what's going on. All right. Again, all of this, the velocity here, all of the velocity in these equations is what is called the equivalent airspeed, EAS, right? Which is the airspeed at sea level. Well, if you're flying at an altitude, if you recall from International Standard Atmosphere, your density goes down as you go up the altitude, and therefore your dynamic pressure changes, the static pressure changes. So, you really have to account for density corrected or compressibility corrected airspeed, right? So you have the different airspeeds here. So you have to make sure that when you're doing the analysis, you're working with the true airspeed, okay? Because that's actually the airspeed that the aircraft at an altitude is experiencing, correct? Um, so again, you have the velocity, you have the maximum velocity at a given altitude in terms of thrust loading. So this, again, it's also a very important equation, right? So you say, for example, you're designing an airplane that should be able to fly at a max speed of this, Well, how do you know that? That's where this equation comes in. Again, this is another constraint equation. We will see a constraint equations and all that later, but again, this just goes to show how important the aircraft performance is before you start designing the airplane, right? So once you're done with the cruise conditions, then you move on to climb performance, right? Basically, you're trying to calculate how faster the aircraft can climb, right? So again, do the free body diagram here, go through the process. What you will find out is that especially in a prop-driven aircraft and even in a jet-driven aircraft, uh, you climb up, right? Your rate of climb really depends on what is called this excess power, right? So excess power is basically, your aircraft needs certain power to remain aloft, but you also have this. The blue line is the max energy available. So the difference basically is called the excess power. And if you want, if you will see as we go through this process, we have the what is called the ROC, rate of climb. You can see that's the power available minus power required, which is basically the excess power. So as you can see that the rate of climb is directly depend on how much excess power you have, right? And here's a nice equation for rate of climb. So again, guys, you're going to see tons of equations as we move along. And it's, again, you may or may not care about where the equations come from. Personally, for me, I like to understand where the equation come from so that I know where and when to use that equation. Right. So again, I listed all of this in here. So please make it a point to go through this document with a fine tooth comb. Okay. So again, I also mentioned some of the specifications for the aircraft, especially for ROC, and also how to calculate ROC max, velocity, and minimum power, and all that. A couple of different methods. Again, we'll talk about that in detail, but for the first homework, you may not need all of these, but this is just here for your reference. Okay, so and you get the turn performance. Again, as I said, you need to know how much G loading or how much the load factor is, that your aircraft will experience while turning. All right. So again, that basically makes it a constraint equation. So the reason, again, you don't have to worry about this. What is this constraint equation? Well, as of now, all you have to worry about is that you truly understand how the thrust, the power, the wing loading, the CD, the CL, all of these connect together. Okay, so you have to know how to calculate the minimum power required. What does the rate of climb depend on? All right, how does the drag polar for an aircraft will look like? So that's everything that you're going to look at in your first homework. Okay, and these equations can help you get there. All right. So I hope, again, this is just a cursory overview. I know that I'm not going into detail, but again, as I said, it's even if I go through all of these equations in a video, you will be bored. Okay, chances are you can go through this a lot faster by yourself. Okay, so that's one of the reasons why I'm not going into like very details into this video, because again, as I said, these are simple Newtonian physics, right? F equals ma, and that's pretty much all there is to it. Okay, but at any point you feel like you're lost, any point you feel like you're not getting some of these equations, please feel free to let me know. Okay. All right. Great. So and then in the next video we're gonna talk about the first homework. All right.